Folks, we are going to take up the spring launcher challenge. It's going to be on YouTube. It's going to be on Sam's channel. So ask Sam if you want that.
What's your channel name?
Ask him later. We only have 9 minutes.
Show them ads. Make that YouTube money.
I'll subscribe.
Yeah, if you're making money off ads, you owe me. Okay, so we launch a spring. We've got to figure out, here's delta X. Here's delta Y. There's theta, which you could calculate. And we've got a couple components for our initial velocity vector. Cos theta, sine theta. The strategy here is to find the launch velocity, work backwards, find the x value that you would need in order to launch the spring to achieve that certain launch velocity. So projectile motion model, PM, gives us that velocity. Okay, so for the x, we have v cos theta, which is the x component of the initial velocity. That will equal the horizontal range over the time interval. And the y, the vertical displacement, is going to equal v sine theta, which is the y component of the initial velocity, multiplied by the time interval plus 1/2 acceleration, multiplied by time interval squared. So my strategy here was to get an expression for velocity, sub one over there, simplify, solve for time, sub back. I find that easier than trying to solve for delta t right off the bat. So I'm going to have v equals delta x over cos theta delta t. Make that substitution over here. So delta y equals delta x cos theta delta t. V goes away. Delta t's go away, sine theta over cos theta is tan theta. So we get the equation delta y equals delta x tan theta plus 1/2 a delta t squared.
So that last delta t squared doesn't get simplified either?
Well, it can't.
Okay.
There's no way to, there's nothing you can do there. Okay, so this is known, you measured it, this is measured, this is measured. This is known, it's an object in free fall, it's 9.8. So then we can solve for delta t. Put our delta t in there. This is known, this is known. So then we can solve for our initial launch velocity. Once we have initial launch velocity, we're looking at two states of the spring. The first state of the spring, state A, will be when the spring is fully stretched. State B will be when the spring just leaves the launcher. Okay? So, do a couple energy graphs here real quick. So we have elastic potential energy at A plus kinetic energy at A. This will equal our total energy at A. There's no friction effects here. Now initially, there's no kinetic energy. All of our energy, mechanical energy, is stored in the spring as elastic potential. Then over in state B, the spring is fully discharged. So there's no more elastic potential. We've dumped all of our elastic potential energy into kinetic energy at this point. And of course our total energy is always the same because energy is conserved. Okay. Even though the spring does displace vertically slightly, meaning that it's going to gain some gravitational, it's only like a 2 centimeter, 3 centimeter rise with the launcher. So for completeness, we could include that form of energy, but it will make no difference when we round significant digits and stuff in the end. Plus your target is of sufficient size to handle error that we don't need to consider that term. But certainly if this were a spring being launched and it was a huge spring being launched along a 1 meter launcher, then it could have a vertical displacement of like 50 centimeters, 60 centimeters. In that case, we would have to take into account that gravitational change. In this case, though, you don't need to solve the challenge. Okay. So we're going to compare energy at state A to energy at state B. Energy at state A is all in the form of elastic potential, 1/2 kx squared. Energy at state B is all in the form of kinetic. So we know the mass of the spring because we can mass it. We know the launch velocity, we just found that. We don't know k, and we're looking for x. So to find k, you have to basically redo the first learning goal with this spring. So use Hooke's law to discover the value of k. So get yourself a ruler, stretch your elastic out there with the spring scale, measure the f, measure the x, then your k value is just going to be that force over x. Do that a few times, or make yourself a little graph, find the slope, whatever, find the k value. You've got the k value, you can solve for the amount of stretch you have to give it initially to launch it at the required launch velocity to achieve the required range.
Okay.